In this example, we have a pendulum which is pivoting about the top point O. We know the weight of the pendulum, we know the radius of gyration about O. And I should say that the pendulum here includes both the thin bar and the block. Then we have a bullet which is coming in with subknown speed, 1600 feet per second, from the right to the left. It strikes the pendulum at a distance h from O, and what we want to do is determine the angular speed of the pendulum immediately after impact occurs. We want to make our system large. Okay, so what I'm going to do is draw an FBD as shown here, which includes both the pendulum and the bullet. Okay, so the forces that are acting on here, we have OX and OY. And so based on this FBD, we're going to use the angular impulse momentum equation to get the answer. And the reason for choosing this is that if I look at my system as a whole, look at the moment about O, the moments are 0, which says that the angular momentum after impact is equal to the angular momentum before impact. Again, the reason for choosing to put everything together is that the impact force, about which we don't care, we don't know what it is, it's an internal force. So if we write down HO for our whole system, we have a 0 for the pendulum. It's initially at rest. And then for the bullet, we have the usual particle expression, R cross mv. I'm going to use x positive to the right, y positive up. So that's m times the vector from O to B is going to be a minus hj. Cross with the velocity of the bullet is going to be a minus vb1 in the eye. So we know that j cross I is a minus k, so this is a minus m times h times b1, so it's in the negative k. After impact, well, first let me identify this as being the contribution to h from the bullet. After impact, for the pendulum, we have mass moment of inertia about O times omega 2 plus R cross mv for the bullet after impact. Like that. Well, the kinematics are such that after impact, and let me call this point down here A. The bullet's going to be there at A. So I can say that the velocity of A, which is the same thing as the velocity of the bullet, is equal to velocity of the hinge point O plus omega cross R. O is a fixed point, so this is omega k crossed with the distance that was h, that's minus hj. So what we have here is a plus omega h in the eye. So this is the velocity of the bullet at time 2. So therefore, HO2 is going to be IO omega 2k, and then we do the cross product. That's going to be a, again, it's a minus hj crossed with velocity of the bullet is omega hi. J cross this is omega 2. J cross I is a minus K. Minus and minus makes that plus. So this is going to be IO plus MH squared all times omega 2. So when we solve this, we set HO1 equal to HO2. At the beginning, we had HO1 as being a minus MHB. I'm sorry, this bad notation here isn't. This is going to be a VB1. So this becomes a VB1. Is equal to IO plus MH squared times omega 2. So from this, we see that omega 2 is going to be equal to minus MH VB1 divided by IO plus MH squared. The negative sign simply means that it's rotating in clockwise sense, and I think that makes sense. IO, we know that in terms of radius of gyration KO. So the mass of the pendulum let's call it MP times KO squared, where the mass of the pendulum is equal to the given weight divided by G. So this is our omega for the pendulum after impact. What did we do? Well, we looked at a free body diagram of the pendulum and the bullet together, concluded that since there's no moments acting about O, H is a constant. Before impact, the only angular momentum we have is for a bullet, that's R cross MV, that end up giving us a minus MHVB1 in the K. After impact, we put in the angular momentum of the bar, of the pendulum, which is IO omega 2, and then M R cross V for the bullet. We find out that the velocity of the bullet after impact is just omega H. We put all that together to find H2. We set H2 equal to H1, solve for omega 2, and then write that in terms of the mass moment of inertia IO for the pendulum.